Hi, welcome to Teardown Tuesday. Today's item is actually viewer submitted. It comes from Lewis Abel from Abletronics in the UK. Thank you very much, Lewis. He sent me this little puppy. It's an EDMI Atlas Mark 10A 3-phase power meter. You know, one of these smart meters that they put on your house these days, and it's got GPRS in it, you know, a 3G thing. It comes with a SIM card, it talks back to base, it monitors all your power consumption, and you know, they don't have to send somebody around to read your meter anymore. They can do it all with one of these smart meters. Now, EDMI are actually an Australian company. Well, they started out being an Australian company. It's manufactured in Singapore, so I'm not sure what the deal is if they're fully Australian anymore, but anyway, I'll claim it. So this is an Australian made smart meter. It's a 240 volt one. It's brand spanking new, still has the unused SIM card in the packet, so pretty advanced functionality in this puppy. Now this one's actually a 240 volt model designed for the Australian or UK market. It's 3-phase, as I said, not just single phase, and it's got a whole bunch of features, and I'll link in the data sheet down below and you can see what advanced capability this does. It does THD and all sorts of weird and wonderful power measurements. Fantastic. So I thought it'd be interesting to crack it open, take a look inside. So you know what we say here on the EEVblog, don't turn it on, take it apart. And I will start out by taking a look just at the spec sheet here, see what we've got. I don't know, it's all sorts of compliance standards. If you're into that sort of thing, check those out. But it's 220 to 240 volt input, although it does operate from 180 to 290 volts input. Burden voltage less than 10 watts per phase. Frequency range, it operates from 45 hertz to 60 hertz. And then the current range, it's got looks like one channel, is that one channel 6 amps, 5 channels 20 amps? I don't know. Current limit is 20 times the maximum current range for 0.5 seconds for those surges. Then our burden power in this case, less than 0.5 VA or 0.5 watts per phase. And it does 4-quadrant energy measurement, imports and exports real and reactive power. It does absolute and 3-phase and per quadrant and all that sort of jazz. And it does frequency, phase angle, power factor, total harmonic distortion, unbalance stuff, and you can do waveform downloads. It's got 5-cycle resolution on sagging and stuff like that. So it records time, date and phase, worst case excursions, programmable trigger levels. Oh man, it's got everything. It's got I/O as well. It's got various relay drive outputs and stuff like that. Really quite neat. Designed to operate over -25 to +60 degrees range. It's 2.1 meg of non-volatile memory, so you can record for 3,600 days, 10 years, with 30-minute intervals across 2 channels. It can do up to 32 channels, interval programmable, 2 independent surveys, whatever they are, instantaneous readings, pulsing inputs, ability to store all of that sort of stuff. And it really is a very powerful little beast. Of course, it's got a built-in real-time clock as well. It's got you know, the rate, adjustable rate output and stuff like that. It's got a big LCD on it. We might power it up after we do the teardown to see how it actually operates, and it's going to have security as well, because these are security and tamper detection and alarms, because these things are smart meters, right? They don't want the consumer to be hacking into these things and doing that sort of thing, you know, and getting cheaper power bills or no power bills. So it apparently has detection for bypassing current and reverse current, provision for sealing with conventional wire or plastic seals, and advanced tamper detection and logging. Well, not quite sure what that is, whether or not, you know, you can hack the components inside. I don't know. Maybe we'll find out. And then it's got various communication options. It's got RS-232, RS-485 multi-drop, and it's got GPRS compatible and compatible with Zigbee and MV90, whatever, don't know what MV90 is. And it's got some software available for the PC which allows you to set all this stuff up. And I'd be very surprised if you couldn't remotely program this thing as well and change all its modes and extract the data and run tests and things like that over the GSM connection as well. And it actually came with the GSM card as well, the SIM card to put in it. So, whew, it's got a lot of stuff. All right, let's take a look at it. It's quite a big unit here, and unfortunately Lewis has had a peek inside. I don't blame him, he couldn't resist. So the calibration, not the, the warranty void and all that sort of stuff sticker has been busted. So it's one big unit as well. All the interconnects are on the bottom here, which we'll take a look at, but apart from that, it's just designed for mounting in a box there. And the user interface, main LCD here, a couple of LEDs which are pulses. It says that it does 10 pulses per kilowatt hour there, so you'd get 10 pulses on that for every kilowatt hour of power consumption, I'm assuming, and that's probably programmable as well. And then we've got a couple of LEDs here, and we've got a couple of push buttons, connect and select, and that's all there is to it. And if we take this bottom off here, we just unscrew this, and whoop, there we go. And there's a couple of terminal blocks in there. They're not the mains power input. We'll take a look at those in a second. But we've got a separate modem down in here, so it's not actually built in. We'll have to do a separate teardown of that, but that is a GSM modem, Intercell SAM, Intercell Proprietary Limited. It's Australian as well. Beauty, I like it. And there's where you whack your SIM card down in there, and it comes with an antenna as well. There we go, just an external antenna, so you can put that away from the box inside your distribution cabinet or something like that. Just a RJ45 on there connecting it, and there's our antenna output. And that is a separate item. That kind of makes sense. They can change that for different countries and things like that, so they can sell the main unit anywhere in the world, and then have different standards for GSM and phone interconnection depending on where you are. And inside the case, they've thoughtfully provided a little pin out here for the interconnects, and there's a it looks like there's a relay output there, some probably opto-coupled outputs there. There's our RJ45, and then we've got our mains input down here. And as I said, this is a 3-phase model, so they've called the phases A, B and C. So we've got phase 1A here going in there and coming out, so it measures the current on that phase, and of course it can measure the voltage relative to the neutral over here as well. So second phase B and third phase C, in and out. And check out the size of these big beefy mains input terminals here, absolutely massive. And I'm not sure where you screw those in. I think you've got to take the this whole cover off to actually get in there. And there we go, that cover just pops off there, and there's your huge big screw terminals down in there. Oh, monsters. And we've got a little jumper here which selects between the internal battery, which is currently connected, and an external battery pack as well. So you just move the jumper across there. I'm not sure why you would want a external battery pack. Now this cover should just pop straight off here because the tamper seal is on the side here. It should just pop off. Now under here I'd expect a, because it is sealed on the side there with that thing, I'd expect there to be a tamper switch under this thing to sense that the cover's removed at a minimum. Whoa, hey, pop goes the weasel. And there we go, ta-da! There's inside the unit. I love how it's just bare. I mean, this is a transparent case anyway. You can sort of, translucent case, you can sort of see through. Aha! There's our micro switch. Ta-da! Love it. So that's our tamper micro switch. So it already knows. There's our internal battery. So it already knows that we've, presumably, if it's actually monitoring, I don't know, you may have to sort of, set it up first and then it's all ready to go. So this is a factory one, hasn't been used apparently, straight out of the box. So not sure if it's configured yet, but there's your micro switch, which disables when you take that front cover off. A couple of MOVs down here by the looks of it. We'll have a look at the board in more detail, and the LCD there's our main processor under there, and the LCD is just standing off the board like that. You don't see that too often. That's rather quite neat. And of course there's second boards underneath because there's no big power stuff on this top board here. This is just the data logging and processing board, I'm assuming. We've got some light pipes there. There's our two little light pipes going up from the LED down on the bottom there, and they just go up through the front panel there. There you go. And there's two other LEDs down here that they went through the big clear window on the bottom there, so those things don't need a light pipe. And we've got our two contact switches over here. It looks like they're just a, yeah, they're just a, oh, there we go. They actually fell out. There's the little rubber. I rather like that. Check it out. They've got that sitting in there like that, and when you push it, oh, that's a really nice switch. Look at that. That's beautiful. I like that. And down near our outputs down here, you can see that we've got 4 outputs, 4 MOVs. Those MOVs are obviously protecting the outputs there, and there's our relay, which went to that one, I believe it was. So one of those relay contacts there would go to there, and there's our optocouplers there. Those 3 optocouplers would be controlling these 3 channels here. We've got more optocouplers over here, so all of this circuitry around in here is, we've got 4 optocouplers there, coupling that over from the digital section, the control section all up the top here, down into this output which drives the RJ45, which goes to the GSM module down there. So that's all optocouple isolated, as you'd expect. Safety first on this sort of stuff. Another optocoupler in there, and that's it. Bob's your uncle. The main processor, there'll be a flash memory device under there as well. Maybe that one down there. It's looking a bit suspicious. So that'd be our 2 mega flash memory perhaps. And we can't get that LCD out because that's actually soldered directly into the board. You may not be able to see that, but I can see it, and that is a TI MSP 430 processor down in there. There's a 32 kilohertz crystal down there. There's probably another crystal somewhere else as well, or that could be the main one, plus there's got to be another real-time clock crystal somewhere as well. So yeah, I don't know, that's probably it for the main processor board. I mean, it's not, you know, there's not a huge amount doing there. We've got our cables connecting down to our main power board down here. That's where a lot of the interesting stuff is going to be. And of course we have the classic LM324. It's actually an LMV 324. Whole bunch of passives around that. It's probably just doing some buffering and things like that. Our batteries are Vada CA half AA size, made in Germany. Oh, brilliant. Now on the power board, well, there's probably 3 boards down there. There's probably a big power one down there. There's probably in that second one down in there. Oh no, that could be an upside down. I see some through-hole components on there, so maybe there is just one big power board under there, but I wouldn't rule out a third board underneath there as well. And on that power board, of course, we're going to see a big beefy current shunt for each, a very precise current shunt for each of the 3 phases. We're going to see you know, some pretty high spec ADC type stuff. You know, like, I don't expect this thing to be terribly accurate down at the watt or sub-watt range. Of course, it's designed to measure, you know, the main current of your house and monitor the main current. So if this thing is 2400 watts, your standard mains outlet, but it can actually go much higher than that, well, you know, if you want, say, 0.1 watt resolution, that's 24,000. You know, if 1 bit is 1/24,000th, you know, you're going to need at least a 15, say, you know, rounded up to, you know, a 16-bit converter there for each channel if you wanted, you know, in the order of sub 1 watt resolution on this thing. It may not have that, may just, you know, may just be happy with a 12-bit converter or something like that, but this would be a pretty, you know, high-spec device. They've spared no expense. I'm sure these things are probably quite expensive. So let's see if we can, oh, there we go. Hey, look, look at that. Look at that. The board just pulls back. It's hinged under here, like it's hinged at the back here with the connectors, and it's just held in place so it doesn't move with that plastic retaining clip there. So you slide it back and ta-da, lift it up, forward and out. Oh, no, something's, oh, there we go. I've got to take this I'm not sure what that cable's doing there. We might find out. But there we go. Ta-da! Oh, we've been mooned. Look at that. Now on this main board, of course, you can see the classic isolated grounds. This is the optocouplers would be bridging these two grounds. Here's our output ground here based on our output connectors down here, and then this is all our logic ground up the top, and then they would have the, of course, have the optocouplers separating those two grounds. Classic, and yeah, they've got a lot of margin on there, that's for sure. Now it looks like this board is directly connected via these screw terminals down into there. Now you'll note that these extra terminals here, which they said do not connect, they do actually, looks like they go through there and then they do connect down into here. So are they like a earth connection or something? But it definitely said, if you have a look down in here, do not connect. No connections to terminals 2, 5, 9 and 13. 2, 5, 9 and 13. So do not connect them, but they are actually connected to something down on the board. So yeah, we're going to have to unscrew this thing. We've got direct connection. Oh, yeah, direct connection down onto the board, which is what you want, of course. You want big beefy connections down into there. And surprised I only had one screw actually. I would have thought maybe they'd have a couple in there perhaps. So interesting to see what form the current shunts take, because I don't think they're mounted on the, not sure if they're mounted on the board. They could be like just free standing underneath, or like actually, you know, lumped right at the back of these connectors, and then they just, and then these are just like the wiring coming up from them or something, the sense lines perhaps. I'm not entirely sure. We'll find out. This is terribly exciting stuff, watching me unscrew. Somebody in the recently commented, oh, why don't I use an electric screwdriver? Oh, come on, that's cheating. I only use an electric screwdriver for, you know, one of those RF die-cast cans or something that have 50 screws on the things. Otherwise you're cheating, and you can't get me just banter on about random crap either. So there we go. That looks like it is going to lever out of, oh, okay, no, okay, they're stuck under there like that, so it looks like you've got to fold, probably fold these up. This could be tricky. Let me work on it, folks. Well, that's pretty obvious. You have to unscrew these in here and they just pop out like so. So now we should be able to pop this board out and pop out, presumably. I mean, there was nothing on the bottom of the case at all, so yeah, I think it just needs some delicate persuasion. Aha! This whole terminal block section pulls out by the looks of it. There we go. Oh, there we go. It all pulls out, the board pops out. It's all rather complicated. Not that trivial. Oh, there. Oh, look at that. Oh, look at that. Beautiful. Oh, that's pornographic. Look at that. And isn't this beautiful? We have 3 current transformers. There's no traditional current shunt resistor as such. They're using these current transformers, and after a tiny little bit of investigation and thought it's obvious why, and here's the reason. And the thing that's driving this is the IEC standard 62053-21 and various other standards. They basically say that these current meters, these smart meters, power meters on your house, can't take any more than 2 watts per phase. And you know, yeah, you've got, you know, 1 million houses hooked up. I guess all that sort of stuff adds up. So determining that maximum power value that these energy meters can consume per phase, a measly 2 watts. So let's look what happens if you've got one of these. We're only going to look at one phase here, okay? So let's have a look if you've got a traditional current shunt resistor. What does that mean? Okay, our current shunt resistor, RS, we're going to have a current flowing through it, and this particular model has 100 amps capability. So let's take 100 amps, and as you know, P equals I squared R. So you rearrange that, our resistance there, so we're calculating, that's RS, and we've got RS here is going to be equal to the power, our maximum power in this case, 2 watts, divided by IS squared, so that's 100 amps maximum capability, or if you design this meter to be 50 amps, you can redo the calculation, but let's use 100, okay? It's going to be in the order, so 2 watts on 100 amps squared is going to give us a value of that resistor of 200 microohms. Absolutely tiny. So, you know, what does that mean? Well, at the not only is that an incredibly low value of resistance, okay, it's going to be, you know, very difficult to implement that. Not impossible, but you can certainly implement that. But what it means is that then at low values of current, instead of say 100 amps, if your house is only drawing say 1 amp on that phase, what does that mean? What's the voltage drop across that shunt resistor? Well, 1 amp, do the math. It's going to be 200 microvolts, basically. And we're talking very small voltages there at very small currents, and that becomes a pain in the ass to measure. So, you know, let alone, you know, trying to measure, you know, 100 milliamps or 50 milliamps or something like that. So what they've done is they've used these current transformers instead of your traditional current shunt resistor. I like it. And they've got 3 big beefy ones here per phase. The output of these current transformers, they're going to convert those into voltage, and they can measure the current as well based on a burden resistor down in there. And also, if you use traditional current shunt resistors, well, you're going to be dissipating, you know, up to a couple of watts inside this thing, and yeah, it's going to heat up, and that can cause potential issues as well. So just something to consider. And the reason that they've gone for these funky current transformers here, because as you can see, you know, there's practically no power dissipation at all in this. You know, basically it's only drawing the current it needs to drive the circuitry and all the measurement stuff, which isn't going to be much compared to a traditional current shunt resistor. So look at these big bus bar, huge big links down in here. They're absolutely massive. So these are the 3 phases here, and we've got our neutral. But of course, having no other connections on there doesn't make sense. So figured it out. What it is you remember these little links that we took off before in here? These are little voltage tap links, and they actually short out. If you have a look down in here, they actually short out the one of the phases here down to this terminal. So you're not supposed to connect this terminal because these links are connected internally. Got these internal links which then connect it through to this trace, which then goes off down in here. So they're your voltage taps going down to all your circuitry over here. And plus there's also another tap which comes off the same pin over to a 3.3 meg resistor on each channel down in there. There's one on each channel. So that looks like that's the other one. Looks like all that stuff up there, it looks like a protection tap. That's just you know, getting the protection devices off. This is probably powering the rest of the circuit as well, but the actual measurement, voltage measurement on each phase seems to be going through this 3.3 meg resistor into this little SOT23 package there, and off to well, I guess the ADC stuff has to be on the main processor board, because I don't see anything on this board down here that looks like it's an ADC. So it's obviously tapped off. We've got a whole bunch of unpopulated circuitry around here. I'm not sure what that was supposed to do. And this link here, which we saw before and we had to disconnect, which goes up to this main board here, it's obviously an isolated voltage tap. There's a little power supply there, and that's going off to power this part of the isolated circuitry down in here on the RJ45 output. So the rest of the circuitry around here, which taps off the 3 phases here, any one of the 3 phases by the looks of it, it is just a mains switch mode DC power supply. There's a switch-in transformer. There's the controller. It's a Power Integrations TNY268GN. So that's a really efficient switch mode controller, like less than 50 milliwatts, no load consumption. So, you know, really one of those eco green ones. So they really do want to get the power dissipation down on these things, of course, to meet those various standards that require these things to have low power. So that powers the rest of the circuitry. It wouldn't need much at all. I mean, they've got big 400 volt caps down in here. You know, it seems a little bit overkill, actually. We've got a common mode choke here, so we've got some filtering over on this side, but it does seem you know, a little bit overkill for the amount of power that I suspect this thing requires. But anyway, I'm sure it needs it for a reason. Once again, they've got lots of protection in here, lots of MOVs all over the place. Looks very well designed. I think they've spared no expense there. The switch-in transformer there is really looks first class. So I really quite like that. And of course, there's that separate winding coming off there I told you about before, which powers the output circuitry that's isolated from this one here, which powers the main circuitry over there. Now, if you look at each channel here, there's 4 components. There's a Zener diode there. It's marked ZD10, but it doesn't look like a Zener diode package. Anyway, I presume it is. And they've just got some, there's a filter cap there, and they've got a shunt resistor there, a burden shunt resistor on the output of the current transformer. And there's not much else to it. There's so you're going to have a bunch of 4 of those per channel. There they are, duplicated, and then there's some extra circuitry in here tapped off this one here. So I'm not sure what that one's doing, but it's going through an optocoupler there. And as I said, I don't know what that unpopulated stuff is. There's a whole row of resistors in there populated, but all that sort of stuff is unpopulated. So there's this board basically is just the power supply and the current to voltage conversion. That's pretty much it. So the ADC must be up under there somewhere, and I suspect it's, well, it's either going to be the internal to the Texas Instruments 430 processor, or it's probably one of those puppies under there, because that's that LM324 we saw previously. So let's have a look at that one. And no, that's just another LMV324. Bummer. And the other 14-pin SO package over there is also an LMV324. So they must be using the ADC in the MSP430 processor. And that's an MSP430 FG4618. And that's actually a mixed signal, one with the higher resolution 12-bit ADC in it. So that's what they're using, just the microcontroller. It's got the internal reference. I don't really see an external reference anywhere under there. There may, yeah, I don't think there is. They're probably using the internal reference there. But as I said, you know, these things don't have to be, you know, hugely accurate right down at the low end. So, you know, the internal reference and the 12-bit ADCs there, good enough. And let's take a look at the current transformer we've got in here. It's a VAC brand, and they make current transformers specifically for electronic watt-hour meters. There it is down there, full electronic watt-hour meters. Brilliant. I like it. The one we've got here is the E4626X501. That's 100 amps primary current capability. They're all a current ratio of 2500. So it's you divide the 100 amps there by 2500. We're going to get 40 milliamps maximum on the output. And they have pretty much essentially a fixed phase error due to, it tells you down here, due to the excellent soft magnetic properties of the VAC core. These are DC tolerant current transformers, and they lead to a negligible small amplitude error, as well as to an extremely low and linear temperature dependence as well. And they've got all the curves in here for all the temperature dependence and stuff like that. And due to the low permeability of the core material, the phase error is typically 4 to 5 degrees, and there it is, 4.73, they're specified precisely. And of course, you can calibrate that out. They're saying either do it in the software or do it in the RC low pass filter. My guess is they're probably doing it in the software because that's the easiest way to do it. Once this thing is already installed and assembled, they would individually calibrate each one of them to basically remove that error. And here's those components I showed you earlier on the output there. There's the primary side, it's just a current transformer. We've got a burden resistor there, which gives us a voltage drop across here, and there's our low pass filter, and off it goes to your ADC. And here's the characteristic curve graph, and it shows various things versus current here. We've got basically the graphs extend from a couple of hundred milliamps down there all the way up to a couple of hundred amps. So this one's only rated to 100 amps, but it can obviously go a bit beyond that. And you can see that we have the amplitude error here, tiny little amplitude error in percentage down in there, and you can see that basically does not change with temperature at all. But you can see the phase angle does obviously change with temperature here, so that would be calibrated. Well, they'll try and calibrate it out at a nominal temperature there, but you can see it's pretty good over the entire current range. I really like it. And of course these things accurately measure the phase angle as well, so they may even be taking the temperature into account. There might be a temperature sensor on the board, and they're, they could compensate for this because it's fairly linear with temperature there. I mean, over an operational range, look of 55 down to sort of minus 10 over that sort of 50 degree range. It's going to change by roughly the order of half a degree error there. So that could be significant. I don't know, you'd have to go through the math and figure it out, do some ballpark calculations, but if it is, you could compensate for that in the firmware, no problems at all, just by measuring the ambient temperature. Now here's an interesting performance graph. It shows basically the behavior of different types of VAC core materials compared to regular 80% nickel iron cores. So they've got their Vitro Perm and Vitro Vac. These are trademark terms for their own core material that they actually use, and they've got an amplitude error here, and you can see theirs is basically flat over the full current range there compared to a typical 80% nickel iron core like that. So much more linear using their Vitro Vac. And the same thing on the phase error as well, of course. Look at that, it's pretty much almost rule of flat, pretty much for the phase angle there compared to the typical 80% nickel iron stuff. So really, they've got some whiz-bang core technology that makes these pretty linear current transformers. I like them. And they've gone to town here. They've even got typical characteristics of the amplitude error versus the primary current over the full current range from 1 milliamp all the way up to past 100 amps there, and you'll note that it's only barely even plus minus 0.25% amplitude error. Well, as for the supposed whiz-bang tamper protection and all that, yeah, they've got the micro switch down here, but apart from that, I don't know if they're got firmware and maybe even circuitry to try and detect whether or not somebody's, well, they've got to try and detect how somebody's bypassing the current. So maybe they're able to do that in firmware somehow. But yeah, I'm not sure. You could probably get in there, and if you're really knowledgeable about these things, you can get in there and hack the shunt values in there or something like that. And I'm not sure if the firmware would be able to know that sort of thing. But of course, once you, to get into it, you've physically got to bypass the micro switch, and then, well, it alerts the utility that somebody's broken into this thing, and yeah, they'll probably wave the finger at you. So I don't think they have to do too much in regards to the tamper protection and stuff like that. it's built in. It'd be interesting to know how they actually detect bypassed current, like in the main box itself, rather than going through here. I'm not actually sure how they would do that. So there you go. That's a look at the main guts of this thing, and it's very well engineered, and it looks like they're spared no expense for this thing, as you'd probably expect. It really is quite nice, and I've run out of time to power this thing up and have a play with it. I kind of wanted to do that, but I might even leave that for another video if there's enough interest in powering up and playing around with it. But I'm not sure if I could use it for anything useful really, because I'm not into doing the high current stuff and things like that, but it might come in handy for something. But I might try and power it up and see if I can have a fiddle around with it later. So I hope you liked that little teardown. If anyone has a schematic or a service manual of this thing, that would be great, because that would reveal a bit more, I'm sure, of what they're doing here. So if you have it, please let us know in the comments. And of course, we can't leave it without taking a look inside the Gsm adapter here. So there's our SIM card module. There's nothing terribly exciting in here at all. Let's flip it over, and there's our wireless CPU, model Q24 Plus. Woohoo! Whoop-de-doo! And there we have a SIPX SP3238. Nothing terribly exciting there, it's just an RS232 transceiver. But all of the magic is done in that Wavecom wireless CPU module. So I'm not going to take that out. That requires to unsolder the tabs on the whole thing and get it out and rip it apart, and couldn't be bothered. So there you have it. There's a teardown of the EDMI Australian, supposedly Atlas Mark 10A 3-phase energy meter. Hope you enjoyed it, and if you got any further info and you want to discuss it, jump on over to the EEVblog forum. The link is below, as well as to various data sheets in this teardown as well. And don't forget, if you haven't already done so, please subscribe to my YouTube channel. Catch you next time.